Hello and welcome. My name is Courtney Bishop. I'm talking about hemodynamics. Today I'll be discussing atrial waveforms, ventricular waveforms, arterial waveforms, the pullback method, and valvular diseases. And we shall get started. We have an atrial waveform. We actually have two different atrial waveforms. I have drawn out for you guys the right atrial waveform, which is on top, and the left atrial waveform, which is on the bottom. And they mostly look the same, but if you can tell with the EKG in the middle, the left atrial waveform is delayed. So normally, during right atrial waveform, the A wave will be around the PR interval, the C will be at the end of the QRS, and the V about the end of the T wave. When we have the left atrial waveform, what happens is it's actually called a PCW, a pulmonary capillary wedge. I will show that a little bit later. So with the PCW, or left atrium, you can tell the A wave is actually going to be at the end of the QRS. And if you see the difference, the A wave here on the top is around the PR interval, and then this A wave is going to actually be at the end of the QRS. So you can see how that section fits right into the PQRST, right at the very end of the T is where everything ends. Here it starts a little bit later and it also ends a little bit later. This is because of the delay when getting your PCW. That's a little better. So, like I said, PCW is delayed. There's not always a C wave. I drew it with a C wave, but there's not always a C wave. Then there is the scale for the right atrial goes like 0 to 8. Typically, the 8 is where you'll see around the A and the V wave. For the left atrial, the PCW, it's a lot higher. So you'll go up to probably about 12. While I go through this project, I'm going to keep referencing back to this. These are our normal values. And if it wants to, there we go. So these are our normal values. So we're talking about the right atrium, and we're also talking about the PCW. So right atrium, the A wave and the V wave are around 8. The mean is about 2 to 6, and we'll talk about that in a second. And the PCW, 12 to 15 is the A wave, 12 to 15 is the V wave, and 4 to 12 is about the mean. So let's go back to this, and like I said, we go out to 8, and 8 is about the average for the A and the V wave, and then for here, 12 to 15 is normally the average for the A and the V wave. So what do each of these, A, V, what do they mean? So A wave, which is at the very beginning, is atrial contraction. This is when the atrium is going to contract and release all the blood that's in the chamber. Then we got the X descent. The X descent is when the atrium is relaxing. So the blood has been pushed out and the atrium's kind of getting back to its normal state. C wave is going to be when the valve has closed. This little bump here is the rebound of the closure. So it's blood kind of going right back onto that valve, creating a little bit of increased pressure, but it's not going to get through if the valve is sufficient. Then we got the X prime, and this is going to be the pulling down of the septum. Then we got our V wave, and the V wave is atrial passive filling. So the atrium is getting filled again, and all the blood's coming back into the atrium via the pulmonary veins. Then we've got the Y descent. The Y descent is ventricular filling, decreased atrial pressure. So this is the valve has opened up and the atria is decreasing pressure. It's getting rid of all the blood going into the ventricles. And it happens again and again, as you can see, same system, and I put it back down here again, A, X, C, X prime, V, Y. And there you go, you have atrial waveforms. Find out the mean of these waveforms. I'm going to use the example of the PCW. So we have, this is the calculations, the A wave plus the trough of the X, divide that by 2. So I put the A wave is about at 12. So that's the A, then we have the trough of the X, which would be right down here. And I actually looked at here, 8, the trough of the X. So this is the lowest point after the X descent. This is where you're going to take that other variable. So we got 12 plus 0, because if we have a scale right here, it's at 0. 12 plus 0, which is 12, divide that by 2. The mean is about 6. And that's nicely done, because when we look about halfway through the 0 to 12, about right here would be the 6. If you slide your finger across, it's the very middle of all of these, which should probably be right about halfway through. You have the equal amount on top as you have on bottom. 6 is right in the middle. And that is our atrial waveform. Secondly, we are going to talk about ventricles. So I've drawn the left and right ventricle. They both look the same, it's just different scale. Left ventricle obviously would be a higher scale, being the fact that there's a bigger chamber, there's more blood being pushed out to go to the rest of the body, versus the right ventricle, which is just going to the pulmonary artery and to the lungs. This is getting pushed out to the rest of the body. So we have, if we look here, we have atrial systole. Again, this is the same thing as the atrial waveform. This is the atrial contraction. And then you're going to go up, and you are going to have where the semilunar valves open, which is like the aortic or the pulmonic valve, which is depending if you're the left ventricle or right ventricle. Obviously, right ventricle be the pulmonary valve opening, left ventricle, aortic valve opening. And then the aortic valve closes and goes back down. Isovolumetric contraction. So from here to here, the dotted lines, this is when there is no blood is moving, the valve hasn't opened up yet. Isovolumetric relaxation. So after all the blood's pushed out, the ventricle is able to relax and start filling again. Again, we got atrial contraction. Here, inside here, same thing, we have the point after isovolumetric contraction, you have rapid ejection. So the blood is, as soon as that valve opens up, the blood is rushing through that valve and going into the aorta or going into the pulmonary artery versus whichever ventricle we're at. Then, after all the blood is immediately rushed out, you have reduced ejection. So there is blood still going out, but it's not the original force, that extreme amount as soon as that valve opens up. Right here is where the valve actually closes. The aortic valve is closing right there, and that's the early diastolic point. So the difference between this, which is the left ventricle I basically drew with a scale from 0 to 200, the right ventricle looks the same but lower pressure. Ventricular systole for the left ventricle is normally about 120, and the typical range is 100 to 140. I have them at 120. If we look, you can see it lines up about 120. Maybe my scale's not that great, but about 120. And then end diastolic should be about 8. Alright, next we are going to talk about the pulmonary artery and the aorta. This is the arterial waveform. This is what the waveform looks like, the arterial waveform. You have the semilunar valve opens up, which is, depending if you're the pulmonary artery or the aorta, should be the pulmonary valve or the aortic valve, opens up. It follows ventricular systole. They should be matching if everything's working well with the valve. Then this is when the semilunar valve closes. This little bump here is really just the aftermath of the closure. It's the blood pushing back onto that valve, creating a little bit of pressure, but it shouldn't open up if the valve is sufficient. Therefore, the pressure will continue to decrease afterwards. Diacratic notch happens, which is right below the little bump, that being the valve closing. This is all of diastole. So to figure out the systole, diastole, and the mean. First of all, systole we can say is The top part of systole, so this is the higher pressure. And when we go across, if we're, say, we're in the aorta, I did scales, so pulmonary, this would be pulmonary artery, which would be around 20 to 30 would be the top. Aorta is 140. If we look here, same thing, pulmonary artery, the systolic, which is the top part, should be about 20 to 30. The diastolic, which would be the bottom part, should be about 10 to 15. And the mean should be about 10 to 20. And for the aorta, 100 to 140 should be systolic, 68 diastolic, and the mean should be about 70. About 25 is the top if we drew a line. Then for the bottom part, here at the diacritic notch cross, we say that's about 10, which normal is about 10 to 15. And we're talking about the pulmonary artery right now. If we're talking about the aorta, it would be a lot higher of a scale. So to figure out the mean, we're going to take it like this is the pulmonary artery. So I said that the systolic is probably about 25. You take 1 of 25. Then you add 2 of the diastolic pressure, which I said was about 10. Then you divide that by 3, and I did the math here for you. 125, which is just 25, plus 2, 10. 25 plus 20, divide that by 3, which is 45 divided by 3, which equals 15. And that works out perfectly because when we talked about it before, we said the mean of the pulmonary artery is typically 10 to 20, and 15 fits right in there. So if you drew a dotted line, which I sort of did, you can kind of see it. If you drew a dotted line in 15, it should be right in the middle of the waveform. The same amount on top, the same amount on bottom. We're going to talk about pullbacks. Pullbacks are basically a method that is used in the cath lab, and it's you put a catheter into the heart and you track through the heart and figure out the pressures and the variant pressures throughout different chambers to see if there's any issues inside the chamber or any issues throughout the valve when you're crossing the two valves, because they all should start correlating at some point. And we'll talk about the different correlations, but there should be a correlation because at one point when the valves open, you have a common chamber between two different places. So the common chamber should have an equal amount of pressure. If it's the systolic, diastolic, or even if it's the mean, there should be some correlation between the two chambers at a given point. So we're going to start with the left side of the heart. The left side of the heart, you gain access into the artery. And in the artery, in the cath lab, a lot of times, there are other times where you can use the radial artery, but as we're learning right now, we're using the femoral artery. Either way, the artery is going to lead to the aorta, and you're going to get to the point that you need to get to. So we go up the aorta with a catheter, and I drew a little line where the catheter is at. You go up the aorta, and we're going to go into the left ventricle, and the little bottom is the sensor of the catheter, and that's right there. So right now we're sensing the left ventricle, and that is going to be displayed on the waveform like this, left ventricle waveform. What we're going to do now that we have this waveform is we're going to pull back the catheter, and I drew little dotted lines, so it's a pullback of the catheter back into the aorta, and the waveform should change. You should see a left ventricle waveform, and then when you pull back, you'll start to see an aortic waveform. This waveform will be correlating to left ventricle because the left ventricle systole and the aortic systole should be the same. So if you drew a line across here, it should be the same. The systoles are the same. So look back at our chart. We will see that the arterial, the aorta, 100 to 140 is the average. Well, look at that. The left ventricle is exactly the same, 100 to 140. We're going to talk about pullbacks from the right side of the heart. So we're going to start on this side. The right side's a little more complex. There's more chambers you can get to from the right side. So we're going to say you gain access in the right side of the heart through the femoral vein. Now, so we are on the right side. We're going to go through the femoral vein. We're going to go up through the superior vena cava and inferior vena cava. Well, we're going to go through the inferior vena cava because we're doing the femoral vein, which comes from down below. Once you go in, the catheter is going to go through the right atrium, down into the right ventricle, up into the pulmonary artery, and over here, the same thing happens on the other side, but you have pulmonary veins that are going into the left atrium. You are going to put your catheter, right now it shouldn't be blown up, you're going to blow it up right as soon as you're in this little pulmonary vein. You're going to blow up the balloon, and this balloon is going to make it so no blood can go into here. So all the blood is going through this other pulmonary vein into the left atrium. Now what happens here is you're in the left atrium. This valve is currently closed. What's going to happen is there's going to be backflow. You're going to have a lot of blood going into this chamber, and blood likes to go to the lower pressure. So there's going to be blood that's going to be coming out here, trying to figure out where else it can go. It goes and it meets up with that end of that catheter, which will actually give you the pressure of the left atrium, because at this point, this is all one common chamber. Now, you are going to pull it back. So this is called the PCW, which is also the left atrial pressure. PCW stands for pulmonary capillary wedge, which you are in pulmonary capillary. We wedge it, therefore the blood, we get the left atrial pressure. Now we're going to go and deflate this balloon. The reason you deflate it is because you don't want to damage this area. The rest of our pullbacks you keep. All the other pullbacks I'm going to talk about, we keep the balloon inflated. But at this pullback, you deflate it because you don't want to damage the pulmonary vein. So we'll deflate the balloon and we pull it back. You see the dotted lines? We pull it back into the pulmonary artery. At this point, we re-inflate it. And there's no blockage. It's inflated, but it's a lot bigger of a space, so we're not blocking anything. But we get a sense of what that pressure is in the left atrium, or the PCW, and then we'll get a pressure that shows the pulmonary artery. So we have PCW. When we pulled it back, we've got the pulmonary artery, and that's that waveform. Now, I said everything has to correlate at some point, because again, it's going to be one common chamber. So the PCW mean, which is in the middle, is equal to the pulmonary artery diastolic, which is at the bottom. So if we drew a line, the mean should equal the diastolic pressure. And taking a look at this, we have the same thing. It shows PCW mean is 4 to 12 equals the PCW mean equals the pulmonary artery diastolic. And you can see 4 to 12, 12, 10 to 15, 12 is in, 10 to 15. So there's that. Then we're going to go. So this is all done at one time, all these pullbacks. So the PCW to the pulmonary artery. Then we are currently in the pulmonary artery, just as we ended over here. Same thing over here. We are in the pulmonary artery. We are going to pull it back and go into the right ventricle. So the pulmonary artery, and then we pulled it back into the right ventricle. Pulmonary artery systole equals the right ventricle systole. Pulmonary artery systole is 20 to 30, right ventricle systole 20 to 30. Next, we were in the right ventricle. Just as we ended the last one in the right ventricle, we are going to pull it back into the right atrium. Cross the valve. Now, right ventricle, this is the waveform for the right ventricle. We pulled it back and we've got the right atrium. Right ventricle end diastolic, which is right here with the right atrial mean. So if we drew a line, it should be right around the middle of that right atrial pressure. The mean is 2 to 6. And if we take a look at this again, we have right ventricle. The end diastolic is 2 to 6. The right atrium mean is 2 to 6, and that is how it correlates. Finally, we have valve diseases. We're going to start with aortic stenosis. An aortic stenosis waveform looks like this. You have the left ventricle and you have the aortic waveform. So, with this, the ventricle struggles to squeeze the blood out because the valve that it's trying to push through is very tight. So what happens is the ventricle pushes and not a lot of blood gets through. This causes a less steep systolic upstroke of the arterial waveform because there's not as much blood pumping through, and this also decreases the aortic systolic pressure, that's the top part of it, because again there's not as much blood that got into the aorta. So that is aortic stenosis. Aortic regurgitation. This looks like this in the waveform. What happens is the aortic valve actually releases blood when it shouldn't be. It's left ventricle and then you have the arterial waveform. What happens here is it rises very rapidly, it rises rapidly as soon as the aortic valve opens. It does trace the ventricle, which is good. Here is where the valve closes, and that's just the blood pushing back onto the valve. Now the problem is the valve is kind of open. So you see this diastolic pressure being lower. It slowly loses a lot of blood, and the blood is being lost back into the ventricle. It's not pushing out to the rest of the body, where you see here it kind of levels off and there's blood that goes throughout the body and stays kind of in the aorta and just kind of goes like that. With this, it's losing a lot more pressure, it's losing a lot more blood, and it's going down in pressure and volume. This can cause issues because this is the blood that's supposed to go throughout the body and supply your body full of oxygenated blood, but instead it's actually going back into the left ventricle. Next we have mitral stenosis. So mitral valve is in between the left atrium and the left ventricle. What happens in mitral stenosis is like the aortic stenosis, the valve is very tight. So the normal looking waveform looks about like this. Aortic, we showed you that it kind of levels off, which is good in that case for the aortic stenosis, minus the fact that it doesn't level off and become one common chamber because there's decreased pressure. Aortic regurgitation, it's going to show that there is a steep decline in blood because it's losing the blood back into the ventricle. Mitral stenosis, you have the blood, the levels start actually up here. In a normal waveform, it's down here and it matches and lines up with the ventricle and it becomes one chamber at that point. So the ventricle is actually following the atrial pressure when it comes to here. This is where the valve closes, so they go their two separate ways. This is still the atrium, but then they meet back up when the valve opens again and they trace each other. They are both right here, ventricle and the atrial waveform. Here is they actually never trace each other because you have a difficult flow of blood. The atrium can't release all of its blood into the ventricle because of the tight valve. So there's more blood in the atrium and it's not releasing it all and it's keeping most of it. Therefore, it never is completely one chamber. There is a tight space, so it's not completely open and there is blood still in the atrial
in the atrium when it should be in the ventricle. The increase in LA pressure, left atrial pressure, is the same reason. I mean, there's a lot of blood in the atrium when it should be in the ventricle because of the tight valve. So that is what mitral stenosis looks like. Mitral regurgitation. So we'll look at that waveform, and it doesn't look too crazy, but then if you look again, V wave in that one is up a lot higher. The V wave should match the A wave at all points. So when you look at here versus you look here, you can see that there is a big difference. So the valve closes, so then the atrial's filling and doing its thing, and what happens is the mitral fails to close blood from the ventricle, which goes back into the left atrium. So the ventricle, when it contracts, opens, and it pushes blood not only to the aorta, but it's also pushing blood back into the left atrium, which is why there is a huge increase here. Because the V wave, as we remember, the V wave is atrial passive filling. So this is when the atrium is filling. So not only is the atrium, the left atrium, getting blood from the pulmonary vein, it is also getting blood from the ventricle, because the ventricle contracts and it's pushing blood both to the atrium and to the aorta, because of that valve not keeping it closed, which ends up increasing the left ventricular end diastolic pressure.